Hello everyone, welcome to our webinar on Basler Autofocus Solution. Thank you very much for joining us today. My name is Lex. I'm the Assistant Sales Manager for Southeast Asia, Australia, New Zealand here in Basler, Asia. And I'll be the moderator of this webinar. Before we start the webinar, here are some information which you need to take note of. Firstly, to provide everyone a pleasant experience, your mic will be muted throughout the whole session. So if you have any question throughout the session, please feel free to drop them in the chat box on your right. We will look through the question and select the frequently asked questions and answer during the Q&A right after the presentation. There will be short polls throughout the webinar, so your participation will be appreciated. Lastly, hands up are also available on your right for you to view or download. Do check it out if you are interested to get a copy of today's presentation slide. Without further ado, please allow me to pass the time to our presenter today. Joshua, over to you.
Yes, hi. So thank you, Lex. So hello, everyone. Yeah, thank you again for tuning into today's webinar. So my name is Joshua. So I'm working as an application engineer who takes care on technical support and customer service in the Southeast Asia and also in the India region. So the topic of today's webinar is how to autofocus your industrial cameras with Buster cameras. So who are we and what are our capabilities? So Basler is a global leader in machine vision solutions, offering a wide range of cameras, sensors, and software for a variety of applications. So that includes industrial automation, medical imaging, traffic monitoring, and so on. So the company has a long history of innovation dating back to its founding in 1954. So here in Basler, we are a team of engineers with extensive experience in developing vision applications and implementing projects, creating custom camera solutions. And we also specialize in embedded vision systems, image analysis, frame grabber and FPGA programming, and system integration for OEMs. So for today's webinar, our agenda, we have about 6 topics for our agenda. So the first one we will go through is the industrial camera and lens. And next, we will talk about the industrial autofocus solution overview. And then also we'll talk on the passive autofocus, CDAF. And also we'll go through some application examples. And then we'll have a live demo after the application example. And then lastly, there will be a Q&A session. Okay, so in every machine vision application, we always strive to get the best and clear possible image. So in the image here, we see a good exposure and a very large depth of field, showing sharp details. And the sharp details here will make it readable for humans and just as well as machines. So next, in this image, we see a very good focus of the camera. But if we zoom into this part here, so you find that the focus is not so clear, right? So we will think that, okay, low magnification or out of focus is the usual potential misconceptions. So in order to achieve high image quality requirements, so the higher the resolution is needed. So thus, the sensor size and interface speed should be taken into consideration. Say example, if I have a large sensor with a high resolution, you require the right interface to fulfill the bandwidth to transfer larger images, right? So another factor here is in terms of lens selection, right? So usually the working distance, field of view are used to determine, the suitable lens, right? So, but however, for industrial cameras, speed and detection precision are oftentimes required. So the depth of field here cannot fulfill the focus on which part that you want to detect. So the factors that will affect the depth of field are the aperture, focal length, and subject distance. So with these 3 points here, if you adjust it, you can satisfy the depth of field requirement. But oftentimes this becomes a challenge to fulfill customers' needs. So getting the right lens becomes a very important topic. Okay, so what we have here are 2 identical images in comparison with different depth of field. So the image on the left has a shallower depth of field, right? And while the right-hand side has a larger depth of field. So as you can see here on the right-hand image, the base, the pins, and also the surface of the pot are very well focused. This is due to the smaller aperture or reduction of 2 f-stops, so from f4 to f8, right? So therefore, this will increase the depth of field. But this, of course, comes with a disadvantage, is that the light is effectively reduced by 4 times. So therefore, the exposure must be increased by 4 times. So from 20,000 microseconds to 80,000 microseconds to get the same brightness. Right. However, in the real-world application, when speed is very important, the exposure time cannot be too long. Because, for example, the vibrations from machines can cause the image to look appear blurry or distorted. So, to get a clear image for such high-speed application, you will need to increase the aperture and then sacrifice the advantage of your depth of field. Okay, so the common challenge encountered for autofocus is that your depth of field, of course, is not enough. Over here, we have a PCB with resistor in focus with multiple other components here out of focus. So although the height of difference between these two is not so big, but due to larger aperture, again, you have to sacrifice your depth of field, right? So you can get the enough exposure time. So the focus here on the PCB or the background, is okay. But if you want to quickly switch focus between these two views, let's say right here you see the background is focused, and on the left hand image here you see the resistor here is in focus. So between these two views, there are limited machine vision related autofocus solution available in the market. So currently, to deal with this demand, the demand of faster speeds, and we have developed an autofocus solution to fulfill market demands. So in the next topic, we will go through the industrial autofocus solution overview. So there are two primary approaches exist in the current market. So one is active and the other is passive autofocus. So while both aim to achieve the same goal, they employ different techniques and have the advantages and disadvantages over each other. Okay, so in active autofocus, which is distance detection based focus, utilizes external signals such as like infrared beams or ultrasonic waves to determine the distance between the subject and the camera. And these signals are emitted and reflected back to the camera or sensors and provides information to the camera to adjust the lens or focus accordingly. Right. So while for passive focus, which is often referred to as image-based focus, relies solely on analyzing the information from the acquired images to determine the focus point. So this is the comparison in terms of speed, accuracy, flexibility, complexity, and cost of different techniques from active and passive autofocus. So first, at passive here, we have a PDAF, so which is a phase detection autofocus. And CDF here stands for the contrast detection autofocus. Okay, so and under active method here, we have a comparison between laser and interferometer. Okay, so for PDF technique, this technique uses a dedicated pixels on the image sensor to detect the different phase the different phase of incoming light waves from different parts of the scene, and the phase difference reveals the distance of the subject, and therefore allowing the camera to adjust the lens focus quickly and accurately. Right. So the advantages here, of course, the fast focusing speed, good accuracy and flexibility, while the hardware cost is relatively low. Okay, so next for CDF, this analyze the scenes for areas of high contrast, which is typically indicates edge and details which adjust the lens back and forth until the contrast is maximized, resulting in a sharp image. So advantages here are simple to implement, or simple and also inexpensive to implement. So it also has a good flexibility, but has a slower focusing speed as compared to the PDAF. right? So one thing I'd like to clarify is the term of flexibility here. So the flexibility is that after, let's say if you have an autofocus design or system that's already completed, it'll be based on the range of working distance that you use. So your working distance and your FOV, have already been determined. So you cannot easily simply change your lens or your sensor anytime you want. Okay. Okay, so for laser autofocus here, this technique, employs a laser beam to measure the distance to the subject. And the laser bounces off the subject and is reflected back to the camera. And the time it takes for the light to travel is measured to adjust the focus. Okay, so this has, of course, a really good speed and accuracy. However, due to the high complexity of implementation, comes with a high cost as well. Okay, so interferometer is extremely accurate here, as you see, and it can reach an accuracy of like nanometer scale, but its speed and flexibility are overall too complex, and it's a big disadvantage. But so this is not really suitable for production or industrial applications, but it's more suited for laboratory level applications. Okay, so the advantage of active focus is that it can detect very distance, means you can move the subject and still get the best focus. To put it simply, it's a real-time detection. So this is a really strong advantage. For customers, this can be a quick setup as the whole system is really designed, and there is no extra processing or load to the PC. Okay, so but again, its limitations, of course, is that the cost is relatively high, and the system complexity is also high, while the flexibility is also low. So you cannot just change the lens or any optical component or hardware component on the go. Okay, so next thing is passive focus. Okay, so with passive focus here, the advantage is that the system architecture is simple. Okay, and the cost is really low and comes with high flexibility. Okay, so meaning can be equipped with different kind of lenses, such as telecentric or even microscopy, and etc. So developing this system, will have three main challenges. So the first involves the autofocus algorithm itself. So it includes the autofocus functionality and lens matching, which requires some extent of effort and expertise. And the second challenge is the speed of focus or refocusing speed. And the third challenge lies in the computational costs, because algorithm calculations and the image capture process can lead to increased CPU usage on the PC. All right, so okay, so now we are into the poll questions here. So over to you, Lex.
Okay, I'll launch the poll question. So what are your key challenges in refocusing your images? So the poll will run for 30 seconds. Please select the option which relates to most to your current situation. It'll take a while to consider and take those as apply to you. Okay, time's up. Thank you everyone for your participation. We'll be now sharing the result of the poll. The majority of you choose that cannot focus due to the target being on different planes. Then followed by high noise. Then insufficient brightness and the limited AF result due to the ill sync and of the lens and the image analysis.
Okay, so let me share my screen.
Okay, over to you, Joshua.
Okay, so next, okay, we'll go into the passive autofocus CDAF. So this is, of course, we talk about the solution that's provided by Buster, whereby we'll be using this technique, okay, for our autofocus solution. Okay, there are many products with CDAF in the market. So, but one drawback of other players is that they can't let you choose the sensor, or you cannot choose decide the lens combination, as most of them are designed primarily as a standalone camera. So if you are looking for a barcode reader, for example, there are there are of course cameras that will meet your requirements in the market. But let's say if you want to use it on testing equipment or other applications, or maybe if you have your barcode size has increased or your working distance has increased, it may not your camera setup may not be suitable. So you need to have more choices of flexibility, as what we mentioned earlier, to match your your standards. Okay, so if you're mainly developing your machine, okay, in terms of contrast focusing methods, right, there are four common solutions in the market. So the first way is to buy a lens controller and then match it with a lens here, or a motor-driven lens to a fixed focal lens, or probably to just the camera. And then the images are transferred from the camera to PC, which is then used to process the focusing algorithm. And then it will send the signal to the controller to control the lens focus. Okay, so over here, you need, of course, a lot more hardware, right? So you need a focusing lens, your lens controller, and additional wiring. Okay, so another complication with this is that with the software effort, right? So you need to develop a program or or algorithm for the lens control. But even if a program is already readily available, let's say if you like to develop your own application, right? There will be a different set of APIs to configure the lens. Okay. Okay, so another solution is the camera itself comes equipped with the lens control algorithm. Okay, as for the autofocus algorithm, you still need to transfer all the images to the PC, and the PC will then send it back to the camera to control, you know, the focus of the lens. So in this solution, you know, its hardware is much less than first method, okay, and yeah, also it's also quite complicated, right? So here you can see that you have to develop an AF algorithm, and then you have to sync the camera, lens, and image analysis. So for the third solution is lens control using image processing card, or such as like a frame grabber. So as the processing board to process the information and the algorithm from the image, and then it will send the instructions to the lens to control the focusing. Okay, so this way the processing is much faster than controlling with PC. Okay, so therefore the focusing can be much faster. And lastly, this last solution, which is relatively new, is what we have developed. So to put it simply, this is a lens which is controlled by the camera itself. So meaning that the autofocus algorithm built inside the camera. So it will be processed within the camera, and then it will directly control the autofocus lens here. So therefore, this helps users to save space in terms of hardware. The only thing is that you need the lens, the autofocus lens, and some cables. So in addition, as for its software, you can control the parameters to achieve the focus effect that you want through Pylon API. Okay, so which is the same API that can be used to control other camera features such as like exposure, your gain, right? And etc. So here, it does not require any like processing from the CPU, and the focusing speed is also quite decent. So all the key challenges are well addressed in the passive autofocusing here. So the challenges here are the autofocus algorithm and lens control, which is controlled by the camera itself, where the algorithm is already built inside the firmware. And the next one is the refocusing speed. So we decided to use liquid lens, which has a faster focusing speed, and CPU loading. So there's no CPU loading required. So the algorithm mostly runs in the camera, and as mentioned earlier. Okay, so part of the autofocus solution here we are currently using is liquid lens from AutoTune. So this liquid lens here helps imaging systems to overcome the depth of field limitations by allowing the focus to be electronically adjusted without requiring any mechanical adjustment or movement. So what is a liquid lens made out of? So liquid lens consists of a tunable lens, which are shape-changing lenses, and the lens are made out of type of liquid, the membrane, and the shape of the membrane can be adjusted with a bobbin voice coil. Okay, so this is all contained wrapped inside a container. Okay, so this lens offers a much more compact, faster, and reliable focus with less tolerance, less tolerance sensitive, and it's more flexible with remote control, and it can be used together with a telecentric and microscopy system. So another thing I would like to introduce is the motorized lens. So motorized lens offers much more features whereby you can electronically control the focus or iris, zoom via an interface such as like a USB. And some even comes with an IR card filter. Okay, and the lens comes with a stepper motor for precise and fast control of the lens. So this is a pure optical lens. So unlike the liquid lens that we mentioned just now, this one is you can just attach this lens by itself with the camera, rather than the liquid lens is actually like an augmentation to your fixed focal lens. Okay, so for use cases and solutions we had provided, you may refer to our main website, right, bustlerweb.com, for more information, or you can download a solution flyer over there for your reference. Okay, so the next thing we'll talk about is some application examples. Okay, so for example, as we just mentioned, the liquid lens can be should be placed in front of your fixed focal lens as shown here in this image. So this is a fun lens configuration, and this configuration has a focusing range that's wider, and it can even focus to infinity. So for applications where you have subjects at different range, or you have a large working distance or varying working distance, or have a large subject for inspections and uneven surface, this can be a very suitable configuration of a camera configuration. Okay. So the next one is by placing the liquid lens to the rear of the fixed focal lens here. So to put it simply, you're adding the liquid lens in between the camera and also the fixed focal lens. So with this configuration, the focusing distance will be narrowed to a certain range, and in a way you will be able to focus more accurately. So with a high diopter degree or focus power, which can make subject near to the lens appear much sharper. So in its main application will be in the inspection of electronic in the electronic industry, such as like the PCB inspection, OCR, or like electronic assembly. So next, for telecentric lenses magnification, okay, so This one has a magnification from 0.15 to 10 times, and inherently this one have a larger depth of field than the other lenses, than conventional lenses. So this is very suitable for applications that requires to eliminate parallax error or to minimize image distortion. So therefore, these lenses can enable highly accurate measurements, particularly useful in applications like dimensional inspection, such as checking for pin bends on a circuit board, or even robotic guidance. So the other one is to use with microscopy. So if you use microscope, you have require higher specifications, such as uh, inspecting insides of the chips or for medical physician purpose. So the magnification here can go up to 100 times, right? So as for microscopes, these are mainly used in medical applications or in laboratories. So the last thing also I'll talk about here is the motorized lens, right? So for this lens, right, again, unlike liquid lens, you can connect this lens directly to the camera. So similar to our fixed focal lens, okay. So for this one, it comes in different specifications. So it has varying focal length where you can choose from. So of course, there are the additional features such as like a zoom control. You can control the focus, and you can also control the iris or the aperture, right? So and also one good thing is that you can actually control the lens remotely, and also this is suitable for like it's also work well during the day or night mode. Okay, so of course, for application scenarios, the main ones would be the ITS, or the Intelligent Transportation System, or even outdoors for like agriculture. And the other one is used in it can be used in a production line or in logistics or even stock checking in supermarkets. Okay, so now going into the live demo. Okay, so hold on, I would like to change my view here. Okay, so yeah, so we like to demo our autofocus solution here. So what we have is a liquid lens from Autotune, and we collaborate with them, which we also develop a very simple and straightforward user interface implanted inside a panel viewer. So you can easily control the lens using this panel viewer here. So to put it simply, we use the camera's I/O directly to control the autofocus lens. Yeah. So what is the advantage here? So if let's say if you were to purchase a third-party autofocus lens, you will need to purchase the cable, the lens controller, and use a separate API to control the lens itself. Whereas there will be a separate API for the camera. So the autofocus solution that we provide here gives a full accessibility of the camera features and can be controlled just by a single API, from Buzzer, which is the panel API. So in this demo, I'll be replaying the live demonstration from one of our colleagues here. Okay, so right here, we have a front lens configuration, right? So meaning we have a camera, you have the fixed focal length lens, and then you have the liquid lens attached in front. Okay, so on the bottom left here is the lens settings. So under lens control feature, okay, and then right here is the focal power of the lens, which is the ability of the lens to converge or diverge the beams of the incident light. So technically, this will help to adjust the focus of the lens. Okay. So you can see here, we can adjust the focus seamlessly using the slider. So right now we can see that the chip, the IC here is in focus. Okay, so the focal power here is a 1.101. So as you can, I think if you have a glimpse of the setting just now, the focal power can range from -11 to +11. So that depends on the lens, liquid lens model. So negative indicates that so negative indicates that your lens is in a concave shape, and positive value here means that your lens is in a convex shape. All right. So so with this shape, it can help to bend the light, and when you increase the power, you're increasing the bending angle. Okay. So in the image viewer on the right here, so we have part of a PCB placed close to the camera, while at the background we have a silicon wafer. Okay, so as you can see, this lens has a very shallow depth of field. So you can kind of notice that on the IC here is very well focused, but the surface of PCB, or you can see on the gold pad here, is out of focus. Okay. So if let's say if I want to change the position where I want to focus. So right now we are just doing some manual focusing here. So if you notice on the bottom here, we have the resolution of the camera. So this camera is actually a 5 megapixel camera, right? So it's 2448 times 2048 resolution. Okay, so wherever I point the pointer in the final viewer, it shows the exact coordinates of your X and Y. Okay, so this X and Y here is coordinates that we can input to the settings here. So over here is your focus X position and focus Y position. Okay, so now it's inputting the values. So if let's say if I want to focus the IC here, so now I know the coordinates is 986 and 330. So I'll input these values into the focus X and focus Y parameters. Okay, so after we set the X and Y position, we will need to trigger the autofocus of the lens. So in order to do that, there's a parameter here called focus auto, right? So over here you can select once, and it will trigger the autofocus. So right now you can see the focal power is 0.925, and yeah, so you notice that actually this is actually a manually controlled focus, but right now we are doing autofocus using the camera's algorithm here. So if you can pay attention to the right image here, so once we trigger, we can see the IC will be in focus. Okay, so yeah, so right now it's much more in focus. Okay, and you can see the focal power here is 1.052. Okay, so this is of course much more accurate, and your IC here appears much more sharper. Okay, also you can see that the focus speed is also relatively fast. So next, you like to focus on the wafer. So input the values or the positions of X and Y. Now we triggered autofocus, and now you can see the wafer, the silicon wafer is in focus right now. So now let's say if you want to focus the surface of the PCB, of course you input the coordinates as shown right here. Okay, so now you can see the PCB surface is in focus, right? So one comparison you can make is that you can see that the IC here is really slightly out of focus. You know, of course, caused by the shallow depth of field of the lens. So yes, this is a very easy to use. As long as these settings, you can adjust these settings inside Pylon. You will have no issues to do so in the Pylon API. So you can set multiple in the API. You can set multiple X and Y positions, and you can just use the focus auto here to start to trigger the autofocus. So one thing I'd like to bring out is the two main factors that can affect the autofocusing speed of this liquid lens. Okay, so first we'll talk about the frame rate. Okay, so currently you notice that the frame rate of this camera is around 75 frame per second, right? So we are using a model is an ACE model is a 2440-75UC. Okay, if let's say if I want to increase the focusing speed, right? So of course the frame rate comes into play because the camera uses images to determine the autofocus, the correct focus. So if let's say if you have a 2 megapixel with 120 frames per second, so effectively you can increase the focusing speed by 1.5 times. So another thing is another thing I would like to point out is the range of the focus distance here. So as you can see here, the autofocus point, lower limit and upper limit. So this is the range that you can specify to the camera in which you want to focus. So if you want, let's say if you want to focus in between 1 cm to 3 cm range, you have to tell the camera that you want to focus in between that range. And you can adjust this range to a much smaller size. And when you adjust this range to a much smaller size or smaller range, you can actually increase the autofocusing speed as well. Yeah. So right here, I'm trying to find the demo. So as you can see, you click once, okay, you can see the autofocusing speed is quite decent, but however, it could be faster. So right here, what he is showing is that okay, we are trying to determine what is the range, what is the lower limit and the upper limit of that range. Okay, so just now he adjusted right now 0.277, which is the focal power required to focus the silicon wafer here. But in order to focus this IC here, you have to increase the focal power to about 1.042, which is this is our upper limit of the autofocusing range. So we can adjust the settings here. So it's just approximate value. So now we try to trigger the autofocus again. So right now it's focusing on the gold pad here. As you may notice, the autofocusing speed has increased as well. Okay, so I would like to talk about the 3 pain points when it comes to the CDAF autofocus. So the first one will be the low light with high gain, or you have noisy image, may cause some issue to the focusing algorithm, or maybe you even have like very low exposure, or even or maybe you have like a low, or thirdly, you have a low contrast environment. Okay, so with these 3 pain points in mind, we actually have no issues trying to run the autofocus algorithm in these 3 conditions that we mentioned just now. So right here, he's showing the gain. We try to increase it to the maximum. However, of course, this is an extreme and isolated case, and so normally customers will not adjust the gain so high. So here we reduce the exposure time, and you can see a very noisy image on the right hand side. Okay, so with this, we can go to the autofocus settings. So yes, so right now we are setting the focus on the Go pad here. So watch watch our autofocus lens able to focus on this Go pad even with high noise environment. Okay, as you can see, yeah, the Go pad is pretty much in focus. So next thing, yeah, okay, and yeah, it's showing that it can be done in repeated successions. Okay, so the next thing I want to show is, let's say if you have a low light condition. So what he did here is that he reduces the gain to from 36 to 0. So now our exposure time is really, really low. So it's the same image here, same view. And we go into our, we manually adjust our focal power here just to show that our autofocus system can actually work under low light conditions. So here we trigger the autofocus. Then we go back to our and adjust our exposure. As you can see, the Go pad here is still already in focus. So yes, it can work well under low light conditions. The next one I want to show is doing a low contrast environment. Okay, so over here, he moved the view to a empty white space here. So you can see there's on the top right corner here, there's a piece of fabric that's on the same level as the plane here. So right now he's setting the focus position right here in the middle. So as you can see, this image here doesn't have any edges or any high contrast points. So our autofocus system is able to detect the right focus for the lens. So as you can see on the top right corner here, the fabric is already in focus. Okay, so since right now we're just doing a demo, okay, I will just only show the basic autofocus features. So I will not go in depth. So if you have any questions or on the features, or perhaps you would like to do some customizations on, you can always contact our support or sales team, and we will be happy to assist you from there. Okay, so that's all for the liquid lens demo. So next I want to show I have to have showed a short demo of the motorized autofocus lens. So okay, in this image in viewer on the right, okay, we have a view of the box, and the configuration here is we have an Ace2 camera, okay, with a motorized lens from Computa. So this is the model that we are using. And this motorized lens has a variable focal length from 16 mm to 96 mm. So as you can see at the bottom here, there's a new parameter called the zoom position. So this additionally, you have the usual settings to adjust the focus. So this is the same way we configure the autofocus that we did on the previous liquid lens. So if let's say you have the command to adjust the focus for liquid lens, you can use the same command to adjust the focus on the motorized lens as well. So basically, it's a common API. Okay, so right now, trying to show the zoom control using Palong viewer here. So right now, he has inserted a value of the 8700 in the zoom position. So right now, it's zooming in to the box, and our field of view is getting smaller while the box appears bigger. So now, of course, the autofocus is the focus is already it's not very good here. So of course, we have to trigger the focus auto here. So as you may observe, the focusing speed is much slower as compared to liquid lens. But of course, since this lens have additional features like zoom or iris control, so a different product will fulfill different set of criteria, right? So here we're basically showing the zoom position, and also we have the iris control, which is this one here, or you can adjust the aperture size by clicking the execute command for iris close or iris open. So close meaning making the aperture smaller, and iris open is to make the aperture size bigger. Okay, so yeah, so if you have any features or requests or questions, you may contact our support or sales team, or please get in touch with us and we can explore a solution for your system. Yeah, so that is it for my demo today. So let me change my screen here. Okay, so yeah. So call back to our poll questions here. Okay, the key challenges in CDAF image acquisition is insufficient brightness, high noise, flat image, lack of contrast, or cannot focus because the image contains target on different planes, or AF results not good enough due to ill synchronization between lens and image analysis. So for the few points, the first 3 points there, we have already highlighted just now in our demo. So it's able to focus without any issues. Yeah, using our autofocus system. Okay, yeah. So yes. So now we are going into the Q&A session.
Thank you, Joshua, for the presentation. I hope now you have a better understanding of our autofocus solutions. We will now take 15 minutes or the next 10 minutes to answer some of your questions. So Joshua, for the first question, which version of Pylon software should I use to enable autofocus function?
Okay, yeah, so for all camera features, including customized autofocus feature, which are already built into the camera firmware, you can use the Pylon software, or you can use your current Pylon software, or you can go ahead to download, the latest and updated version of Pylon software from our website for free. So, but please keep in mind that this autofocus feature is a customized feature. Therefore, it's not a default or available feature in a standard Buster camera product.
Okay. The next question, can Bustler camera work with other lens brand beside Optotune and CBC?
Um, yes, perhaps. So on the condition that the liquid lens or the motorized lens supports the UART or I2C protocols, then you're able to control the lens through that using that communication protocol.
Okay.
Hmm.
Okay, for the third question, can the set be sold separately? For example, I wish to purchase the autofocus camera from Bustler, but the liquid lens from elsewhere. Do you offer loaner set for testing?
Yeah, so yeah, we do offer a loaner set for testing, or alternatively, you can purchase, purchase separately. So, however, we will recommend that you purchase the whole solution set for easier and better after sales services. So, you as a customer can benefit from the peace of mind for getting the solution directly from Buster
Mm.
and being fully covered. Yeah. So, Buster offers uh, different autofocus solutions. So please, as mentioned just now, we have liquid lens and also a motorized lens. So please contact our sales engineers for project analysis and evaluation first. Then we will be able to arrange a suitable solution for you. Yeah.
Okay, got it. Okay. Next, will the temperature affect the focusing accuracy of the liquid lens?
Temperature, yes, definitely. But of course, the liquid lens, of course, offers a compensation over increased temperatures. So, in our case, the lens that we are using has a temperature range between -20 to 65 degrees Celsius. So, if the working temperature falls within this range, yeah, the liquid lens should be able to perform normally. Yeah.
Okay.
Mm.
So another question coming is how to tell when the camera is focused?
Mm. So yeah, so I think for this we have an autofocus and events. So event is basically it's a feature in the camera where it stores information such as like frame start, timestamp. It can also store information like this. So like the autofocus and event here. So if the camera is able to, I mean, if the camera has done its autofocus, right? So you have a flag
Yeah.
or you would mark an event, and you can actually retrieve it through the API to know the condition of the autofocus or to know the status of the autofocus.
Okay,
Yeah.
thank you.
Mm.
And we have the last question is can I use NIR or SWIR camera with liquid lens?
Yes, yes. So yeah, the standard liquid lens supports a wavelength between 400 nanometer to 950 nanometers, and there's also options that works with as yeah, with wavelength range between 850 nanometers to 1600 nanometers. Yeah.
Okay. Yeah, thank you, Joshua. Thanks, everyone. I hope you enjoyed this session with us. Unfortunately, our webinar today is nearing the end. So for your convenience, this webinar has been recorded on-demand viewing. There will be also a survey at the end of the session. So do remember to fill it up as it helps us to improve future webinars. Stay updated on our upcoming webinar topics by scanning this QR code or visiting bustlerweb.com. Again, thank you for joining us today. Stay tuned and see you next time.
Okay, see you. Thank you. Bye bye,
Yeah,
everyone.
thank you.